Okay, so chapter 2 is all about frequency distributions. So, a frequency distribution is going to be an organized tabulation of information that shows the number of individuals that are located in each category on a scale of measurement. Frequency distributions can be displayed as either a table or a graph. These distributions are also going to always show a set of categories that make up the original measurement scale, and it will show a record of frequency, number, and of individuals in each category. A frequency distribution table is a structure of a frequency distribution. It will show categories in a column, ordered from highest to lowest. It will also show the frequency count, and next to the category, which is the X values, it's going to show the sum of the population. It'll help you commute the sum of scores from a table and convert that information back to original scores. And a proportion is going to measure the fraction of the total group that is associated with each score. So the proportion would be P equals F over N. It's often called a relative frequency because they describe the frequency in relation to the other numbers. A percentage is going to express a relative frequency out of 100. So the percentage is going to be P times 100 over F and N times 100. And this can be included as a separate column in a frequency distribution table. So here's an example of frequency, proportion, and percentage that is displayed in table form. And our first learning check will be use the frequency distribution table to determine how many subjects were in the study. So how many total people participated in the research study? Was it A, 10, B, 15, C, 33, or is it impossible to determine? I'm going to give you guys a few moments to figure out that answer. And then the correct answer is going to be 10. And if you add up all of those numbers under the F column, that will equal 10 to let you know how many participants were in the study. Our second learning check is a true-false question. True or false? More than 50% of the individuals scored above 3 in the frequency distribution you see. True or false? The proportion of scores in the lowest category was 3. Take a few moments and look at that distribution to try to see if you can determine whether these statements are true or false. And the correct answers are true. There are 6 out of 10 individuals who scored above 3, and that would be 60%, which is more than half of the people who participated. And you can see that just by looking at those F scores that were above 3, 4, and 2. So you got 6 out of 10. And for the second question, it is false. A proportion is a fractional part. So 3 out of 10 scores would be 0.3. So the next thing we need to discuss is group frequency distribution tables. So whenever we have these tables, if the number of categories is very large, they are combined into or grouped into intervals to make the table easier to understand. However, sometimes when this happens, information can be lost. Individual scores may not be retrieved. The wider the group interval, the more information that could eventually be lost. So there are a few guidelines for whenever we group frequency distributions. First off, if there are 10 or fewer class intervals, that needs to be what is typically the case. And anytime there's more than that, you want to use good judgment. The width of each interval should be relatively simple. So things like 2, 5, 10, or 20. The bottom score in each class interval should be the multiple of the width, and all intervals should be about the same width. So whenever we are looking at real limits and frequency distributions, we want to be able to construct, being able to construct either the frequency distributions or the group frequency distributions for discrete variables is fairly easy to do. The score will be an exact score, and individuals with the same recorded score will have the same measurements. In addition, constructing frequency distributions for continuous variables requires understanding that a score actually represents an interval. So a given score actually could have been given any value within the real limit, within that interval of scores. The recorded value was often rounded off to the middle value between the score's real limits, and individuals with the same recorded score probably differed slightly in their actual measurements. Constructing group frequency distributions for continuous variables can also require understanding that a score actually represents an interval. Consequently, grouping several scores actually requires grouping several intervals. So those limits of the grouped class intervals are always 1 unit smaller than the real limits of the group class interval. So I want you to think about why that might be the case. Here is our second learning check. A grouped frequency distribution table has categories intervals 0 through 9, 10 through 19, 20 through 29, 30 through 39. What is the width of the interval from 20 to 29? What is the width of it? Is it going to be A, 9 points, B, 9.5 points, C, 10 points, or D, 10.5 points? Take a few moments and think about the correct answer. And the correct answer is going to be 10 points, because you would look at 29.5 minus 19.5, which would give us 10. And that's going to tell us the width of that interval. What's right above, what's right below. Here are also 2 true-false statements. True or false, you can determine how many individuals had each score from a frequency distribution table, or you can determine how many individuals had each score from a grouped frequency distribution. So you can determine how many individuals had each score from a frequency distribution table. That is true. The original scores can be recreated from the frequency distribution table. The second statement, you can determine how many individuals had each score from a grouped frequency distribution, is false. Only the number of individuals in the class interval is available when the scores are grouped together. Now let's switch gears a little bit and talk about a frequency distribution graph. This occurs when we have pictures of the data that's organized in tables. They can have 2 axes, an X and a Y, and these are typical categories of the measurement scales that increase from left to right for the X axes and from top to bottom for the Y axes. When it comes to general principles of frequency distribution graphs, both axes should have a value of 0 where they intersect, and the height should be about 2/3 to 3/4 of the length. When it comes to measuring, graphing data, you would do so on a nominal, ordinal, interval, or ratio scale, which we'll talk about more in depth. What those things are, we already talked about that in chapter 1. You have to look at whether or not it's discrete or continuous, and whether it describes the sample or the population. Graphs for interval or ratio data require numerical scores. They represent all scores on the x-axis from minimum through maximum observed values, and include all scores with frequencies of 0. You can draw bars above each score to show the height of the bar, which corresponds to the frequency for that category. For continuous variables, the width of the bar extends to the real limits of the category. And for discrete variables, each bar extends exactly half the distance to the adjacent category on each side. So here's an example of a frequency distribution histogram that is found in chapter 2 on figure 2.3. You can see the frequency distribution and how it is shown. When it comes to graphs for interval or ratio data, you're going to have group data into class intervals. You can draw those bars above each grouped class interval. The bar width is the class interval in real limits, and the consequence of that could be apparent limits are extended out 1/2 score unit at each end of the interval. So if we take a look at figure 2.4, we can see an example of a frequency distribution histogram for group data. So we can see that we've got those intervals present. When it comes to graphs for interval or ratio data, a standard histogram can be made into an informal histogram. You can create a bar of the correct height by drawing or stacking blocks. Each block represents one individual, and therefore those block histograms can show the frequency count in each bar. So here's an example of a frequency distribution block histogram. When we're constructing a polygon, we can list all numeric scores on the x-axis and include those that also have a frequency of 0. Draw a dot above the center of the interval that's going to correspond to the frequency. Connect those dots in a continuous line, and that can be used to show the group frequency distribution data, such as what you see here. This is going to indicate the polygon. Here's a polygon for group data. When it comes to graphing nominal or ordinal data, for non-numerical scores, you're going to use a bar graph, which is similar to a histogram, shows the spaces between adjacent bars that indicate discrete categories without a particular order, which is nominal, or non-measurable with non-measurable width, which was ordinal. So here's an example of a bar graph. Here's an example of the use and misuse of graphs. When it comes to graphs for population distributions, if a population is small, scores for each member are used to construct a frequency distribution graph, like a histogram and a bar graph. If a population is large, the scores for each member are not possible. So the graphs have to be based on relative frequencies that are used, and the graphs might use smooth curves to indicate exact scores that were not used. It probably is going to indicate a normal distribution, which is symmetric with greater frequency in the middle, and common data structures for many variables. Here's an example of a bar graph of relative frequencies. And then there's an example of the population distribution of IQ scores, which is a normal distribution. We know that the average IQ score is 100. That's the mean. It's right there in the middle. And then as we go one standard deviation, which is 15 points away from the mean, we get to above average, below average, and low average, and above average, genius, intellectually disabled categories as we continue those standard deviations. When it comes to the shape of a frequency distribution, researchers describe a distribution shape in words rather than by drawing it. A symmetrical distribution is going to have each side that mirrors the image of the other. A skewed distribution is going to have scores that pile up on one side and taper off with the tail. So when the tail is on the right side, and all the scores are mostly high, that is a positive skew. And when the tail is on the left side with low scores, that is a negative skew. And here are some examples of positive skews and negative skews and what a symmetrical distribution would look like. So for our third learning check, what is the shape of this distribution? Is it symmetrical? negatively skewed, positively skewed, or discrete? Take a few moments and think of the correct answer. And the correct answer would be positively skewed because that tail is on the positive end of the distribution. And here, of course, is also a true-false, couple of true-false statements. First one, it would be correct to use a histogram to graph paternal marital status data, like being single, married, or divorced, from the Treatment Center for Children. And the second statement is it would be correct to use a histogram to graph the time children spent playing with other children from data collected in the Children's Treatment Center. Take a few moments and think of the correct answer. And for our first choice, it's going to be false. Marital status is a nominal variable and a bar graph is required. And our second statement is going to be true. Time is measured continuously and is an interval variable. When it comes to Steve and leaf displays, this is going to be a simple alternative to a group frequency distribution table or graph. Each score is separated into two parts, a stem and a leaf. The first digit or digits is called a stem. The last digit is called a leaf. For example, if we had x equals 85, this could be separated into a stem of 8 and a leaf of 5. Every individual score has to be identified. So for learning check 4, for the scores shown in the stem and leaf display, what is the lowest score in the distribution? Is it A, 7, B, 15, C, 50, or D, 51? Take a few moments and figure out the correct answer. That correct answer is going to be D, 51. And here are a couple of true-false questions as well. Any frequency distribution is suitable for a stem and leaf display. True or false? And the second question is a score of 54 is displayed as 5 stem and 4 leaf in a stem leaf display. Those correct answers are false. A stem and leaf display is a simple alternative for a group frequency distribution. And then for the second one, it's true. The first digit 5 is the stem, and the last digit 4 is the leaf. So I hope all of this explanation has helped in your understanding of frequency distributions.